Groth will tell us about pairing-based, succinct, non-interactive zero-knowledge arguments.
Thank you. Yes, so let me start by giving a bit of motivation here. Okay, so imagine, for instance, you have voting scheme. Okay, so the voter knows some vote, right? And in order to keep it private, the voter will encrypt this vote, right? And then send the ciphertext to the election authorities. And the election authorities, they will somehow tally these votes without decrypting any individual votes. Now, this is fine for keeping the vote private of the individual voters, but there's a problem in the sense that you may actually have election fraud, right? So suppose the voter just really dislikes Bob, right? The voter might encrypt something like minus 100 votes for Bob. Okay? And this is not something that the election authorities would be able to check, right? Because it's encrypted and they can't actually see what's inside, and they don't decrypt individual votes, they just decrypt the result. Okay, so they might very reasonably ask, you know, is this encrypted vote actually valid or not? And a solution to this is to use a non-interactive zero-knowledge argument. Okay, so the voter sends the ciphertext to the election authorities and also sends a non-interactive zero-knowledge argument that the encrypted vote is valid. Okay, and what does this give us? Well, the election authorities are happy because this voting scheme has a soundness property which guarantees that the vote is indeed valid. Okay, and the voter is happy because it has a zero-knowledge property that guarantees that the vote remains secret. The only thing that the election authorities can learn from this argument is that the vote is valid, but they don't learn what is the vote. Okay. So more generally, we'll be looking at statement which is X belongs to some NP language L. Okay. And there will be a prover and a verifier. So the prover is the one trying to give the argument and convince the verifier that indeed X belongs to this language. And in a good run of the protocol, the prover has a witness to this fact. Okay. There will also be a common reference string. Okay. So some distribution of bits. Okay. It could either be a uniform distribution of bits, or it could be some specific distribution of bits generated in some trusted way. Now, it would be nice to do non-interactive zero-knowledge arguments without a common reference string, but we don't know how to do that. We need some sort of setup assumption. Okay, so this is the setup, right? Now the prover can send an argument that hopefully will convince the verifier. And again, we have these two essential properties, soundness, but this argument, if it's valid, it convinces the verifier that the statement really is true. And it's zero knowledge, that it doesn't reveal anything but the truth of the statement. Okay, so in particular, it doesn't reveal what is the witness that the prover knows. Just reveals that X belongs to the language. Okay, so what I'm going to talk about is non-interactive zero-knowledge argument for circuit satisfiability. So the statement will be some circuit, and the claim will be that there's some input to the circuit that will make it output 1. Okay, and this is an NP complete language, so if we can do this, we can do all languages in NP. The common reference string will have a special distribution. It's not uniformly random. It has some special distribution. It's verifiable that it has this special distribution, but you do have to generate it somehow with this special distribution. And somehow the prover and verifier will have to get hold of this common reference string. The non-interactive zero-knowledge arguments will be publicly verifiable. So you can have two flavors here. You can have privately verifiable arguments or publicly verifiable arguments. And there's some advantages to having publicly verifiable arguments in the sense that if it's publicly verifiable, anybody can verify it. It's not just one particular verifier. So you can take this non-interactive zero-knowledge argument, you can copy it, you can send it to different verifiers, and then they can all verify the same argument. Okay. And these non-interactive zero-knowledge arguments I will talk about, they will have constant size. So that's kind of the main result here, that you can actually convince the verifier, even on a very large circuit, you can just give a constant size argument, and that will convince the verifier.
Size of security parameter, like constant number of group elements?
Constant number of group elements. And there's a bit of a trade-off here, because the arguments will be constant size, but the common reference string will be long. And then you can trade between those. You can get shorter common reference string, longer arguments, and in that case you can get both of them to be sublinear, so they're both smaller than the circuit.
Long in the sense as big as the circuit.
Bigger than the circuit.
Yeah. So here both of them are sublinear, or one is long? Sorry, I didn't.
Okay, so you can have, there are two settings, okay? One where you have a long common reference string.
So long
And
is circuit size.
Exactly. And on the other hand, a constant number of group elements for the argument. The other setting is where they're both sublinear, but not constant, right? But some sublinear.
Okay, but sublinear, is it also sublinear in, let's say, the witness size?
No, circuit size,
Circuit size.
yes. Okay. So the main point here is actually, so we already know how to do this in the Fiat-Shamir heuristic, right? So we take an interactive communication efficient argument, that's public coin, right? We use a cryptographic hash function to compute whatever challenges the verifier wants send back. And now we have something that's non-interactive, okay? But there are actually examples of non-interactive arguments made with a Fiat-Shamir heuristic that are provably insecure, okay? So the goal here is to do that without using the Fiat-Shamir heuristic, without using a random oracle model, and get something based on assumptions that may actually be true in the real world. Okay, so the argument will have perfect completeness, which means that if the statement is true, the prover can convince the verifier. We'll have computational soundness, so it will be hard for a cheating prover to convince a verifier about a false statement. And we'll have perfect zero knowledge, will not leak any information whatsoever about the witness. And I just want to note that this is adaptive soundness I'm talking about, right? So we actually, the two variations of soundness, one is non-adaptive, where you just, and where the adversary chooses a false statement, an unsatisfiable circuit, without seeing the common reference string. Or there's the adaptive version where the adversary can first see what is the common reference string, and then choose the false circuit and try to cheat. Okay, so the adaptive soundness is the strongest version, and that's what we're going to get. Okay. So there's already been quite a lot of work on non-interactive zero-knowledge arguments. So I've tried to put up a comparison table here of all the ones that are based on pairings. Okay. So you have proofs that are linear in the circuit size, so n is the circuit size. So on the top you have Groth of stuff high, which has linear size proofs based on the subgroup decision assumption. You can also base it on other assumptions. Then you have Up and Fair, they had a construction based on the discrete logarithm assumption and a knowledge of exponent assumption.
Sorry, so n is the size of the circuit, sorry, just to make sure. So n is what size of the circuit?
That's the size of the circuit, okay? So it's an n-gate circuit.
And the witness has independent size, which could later, you don't
I mean, we don't know what the witness size is, right?
less than n.
Yeah.
So, okay. I mean, I'm curious how, for example, your result relates. So we know using fully homomorphic encryption, for example, that you can do everything that in
With witness
everything
size.
that relates only to the size of the witness, not
Yes.
the computation.
Yes, yes.
Okay.
And I think this is really an orthogonal direction, right? Because if you have a circuit which has a large witness, right? I mean, the witness might be as large as the circuit, right?
Exactly.
Then you really get something here, right? On the other hand, if it's a circuit which really has a very small witness, right, or only very few input gates, then you would get better efficiency with fully homomorphic encryption.
Just to pass this thing, like the white stuff, like refers to the things that are above it?
Yes. Okay. Okay. Okay, so that was up and fair. That was also linear size arguments, and based on discrete logarithm problem knowledge of exponent assumption. And then we have these constructions here, one by myself, which has constant number of group elements, and one by Helga Lippmann, which also has constant number of group elements. Okay. And then another option would be to use an interactive proof. You use a Fiat-Gervais heuristic to get a non-interactive zero-knowledge argument. In that case, you can get even lower complexity than the cubic root of the circuit size. Okay, so there's a price to pay here, right? Because I'm actually using these knowledge of exponent assumptions, which are non-falsifiable assumptions. So I'm using some quite strong assumptions to get this. Okay, somehow that's in the nature of the problem. So the proofs by Abbe and Fehr showed that you cannot get perfect zero knowledge with a direct black box argument without having some kind of strong assumption. Gentry and Vicks showed that you cannot get sublinear size without having some kind of strong assumption. Yes.
So the Q, CPDH, and so all these assumptions are also knowledge of exponent type assumptions.
Right. So more precisely, the QPKE, that's power knowledge of exponent assumption. That's an extractor assumption, and this one is an extractor assumption as well. These two are standard computational assumptions. Okay. So I kind of try to organize this in what I think is the most reasonable assumptions on the top right and the most risky assumptions on the bottom right. So this work is of interest if you don't believe in the random oracle model, right? But you still want to get something that's sublinear.
In terms of this sublinear thing, what is the relation with all this PCP-based kind of stuff? PCP-based CS proofs, or it's different? I mean, it seems like whenever the proof is sublinear, you should compare with some of the PCP stuff. But
they use Fiat-Gervais, right?
Sure.
I see. You're saying because they use random oracle.
Yeah. So there's actually some work also trying to combine that with these techniques and get something that's even more sublinear, right? But it's not pure pairing based, and I'm kind of so I didn't include that just because there's a lot of stuff that you could put in the table.
But you're saying the comparison will be with the last line. So the last line is the most closely related to PCP because it uses Fiat-Shamir.
That's true, yeah. So you could get below this. I picked this one because it's pairing based and I'm comparing pairing based, and because it's actually efficient, something you can implement. You don't get into conflict with these large constants that you often have in PCP constructions. Okay, so this is kind of what the field looks like. What I'll try to do now is to explain how to get these sublinear non-interactive zero-knowledge arguments. Okay, so they're all pairing based. So I'm assuming that we are working in some bilinear group. Okay, so we have G and a target group GT that are cyclic groups of prime order P. Okay, I'll assume we have a pairing that maps pairs of elements from the base group G into the target group. Okay, and I'll assume that these group operations deciding membership of the groups compute in this pairing is efficiently computable. And I'll make two assumptions. So one is a standard computational assumption. Okay, it says that we'll give as a challenge G and then G to the X up to G to the X cube, where X is chosen at random. Okay, and then G to the beta, G to the beta X, so simply all this multiplied with beta in the exponent. Okay, except for G to the beta to the Xj. Okay, and then the challenge is to compute what is actually G to the beta Xj. Okay, and the claim is this is hard to do for a computationally bounded adversary. And you can prove this holds in the generic group model. Okay, so this is as kind of standard assumption, okay? The other assumption is not a non-standard assumption in the sense that it is an extractor assumption, okay? So what this assumption says is that, well, if we have g to the x up to the g to the x q, and we have the same things raised to alpha, so g to the alpha x up to g to the alpha x q, and the adversary computes two group elements, c and c hat, such that c hat is equal to c to the alpha, then there's only one way the adversary could do that, basically taking these group elements and raising them to some known AIs, okay? So the assumption is that if the adversary computes c and c to the alpha, it's because the adversary actually knows some values a naught, a1 up to aq, and it simply computed c as these powers here of x raised to the AIs, and over here it took the g to the alpha and powers of x and raised those to the AIs. Okay?
Yes, can you actually prove any of those knowledge of exponent assumptions in generic group model, or it's meaning?
Yes, so this holds in the generic group model.
Oh.
Okay. So that's kind of, I think that's the strong assumption that we're going to make here. But as I said before, if you want to get sublinearity, you need to have some kind of strong assumption. Okay, so the construction uses a commitment scheme, okay? So the commitment scheme is basically has a commitment key which is g and g raised to powers of x, okay? And in order to commit to a bunch of elements, a1 through aq, we compute g to the r and the product of the gi's raised to the ai's, okay? So this is really like a standard Peterson commitment scheme, okay? And it's a perfectly hiding commitment scheme. If you see this group element C, you have no clue what is these AI values, right? Because there's this G to the R, so basically what you're getting back, no matter what the AI values are, you get a random group element. Okay, so the commitment doesn't reveal what are the committed values. And then it's computationally binding. It's hard to find two different openings of this commitment, so it's hard to find a different R prime and AI primes that would give us the same commitment, okay? So once we have this commitment, somehow the prover can only have one set of contents to this commitment, one set of AIs in mind. Okay. Now one very important factor with property of this commitment scheme is that no matter how large Q is, right, the commitment is just one group element. So we really commit to a long vector of elements with just one group element. And that's what kind of will give us our sublinearity in some sense, right? Because we can have this huge vector, we can operate on this commitment, but it's just one commitment that the verifier will see, which is one group element. Okay. So actually what we'll be working with are knowledge commitments. Okay, so I'll extend the commitment key to also have these g hat values, which are the g's raised to alpha. Okay, and what we'll do is we'll do the commitment we had before here, and then we'll do the same with the hat values. Okay, and this is something that's very easy. You can actually use the pairing to verify that this is a correctly generated commitment.
Why were the previous ones not knowledge commitments?
So, okay. So one way you could generate C, for instance, is you could just pick a random group element.
Oh, okay.
Right? And then obviously you don't know what's inside the commitment. Okay? So that's why we are adding this C hat value as well, because now by the Q power knowledge exponent assumption, the only way the prover could do this is if it actually knows how to open these commitments. Okay? So now we have a commitment which is just two group elements to a vector of values a1 through aq, okay? And the verifier is guaranteed whenever it sees this kind of commitment that the prover knows A1 through AQ. It knows how to open this commitment.
This exactly right. So you're saying for every adversary that returns a commitment, there is a simulator that.
So,
Extractor.
so I'm saying that for every adversary that returns this pair CNC hat, there's an extractor which gets the same input and produces CNC hat and also the A1 through AQ.
Right. And none of these things can check if the commitment is valid or not, right? So the extractor is given CNC hat.
Yeah.
With it, all commitments are valid.
When you verify the pairing,
You verify with a pairing here. So actually you can verify here that C hat is the same as C to the alpha. Okay? So you know in that sense that it's a correct commitment.
But what about this R's? Oh, it's the same R, because
Yes.
you're using the same R. So it's not perfectly hiding anymore, obviously. It is perfectly binding now.
It's perfectly hiding.
Can't be perfectly binding.
What do you mean?
Well, so
but you had
it's
this
said because all these G hats are just G to the alpha, right? So you could think of it another way, right? Just say C is perfectly hiding, right? And now we just raise it to alpha, right?
Oh, I see.
Still perfectly hiding. There's no extra information given. Okay. Okay, so what we have so far is we have this perfectly hiding commitment scheme, right, which just uses two group elements to commit to a set of Q values, A1 through AQ, right, and it guarantees that the prover actually knows what these values are. Okay, we'll need various properties from this commitment scheme. One is that it's homomorphic, okay, so if you take these two commitments and you multiply them together, you get a commitment to the sum of the values. So basically what you can do now is in a sense to do verifiable computation, right? The prover can send two commitments to the verifier can multiply them together. Now the verifier knows that inside these commitments is the sum of these two vectors, right? But it still sees very little communication, just sees constant number of group elements. And that's one of the properties that will be very useful. We'll need three more things, okay? So some tools that we can use to build non-interactive zero-knowledge arguments, okay? So one of them is a restriction argument, which basically allows you to say that there are only certain values of these A1 through AQ that can be non-zero. So you can pick a set S, and you can give an argument that within that set, the AIs may be non-zero, but outside that set, they're going to be zero, okay? So one example would be to take the set from 1 through n, where n is smaller than q, right? And if you give this kind of restriction argument, you guarantee that the commitment is on the forms of GS to the AIs for I up to n, but an plus 1 up to AQ, afterwards, they're going to be zero.
How do you do it? You're saying you can prove it.
Yes, so and I'll get to how to do that later, but right now I just want to put in place the building blocks that we're going to use. Okay. Another one is a product argument, okay, which says if we have three commitments to respective AIs, BIs, and UIs, we can prove with just a constant number of group elements that the UIs are the same as the AIs times the BIs. Okay, so we can give an argument that in parallel says, okay, we have a vector of AIs, vector of BIs, vector of UIs, and the UIs are the entry-wise product of the A vector and the B vector. And finally, we'll need a permutation argument, which says if we have two commitments to respectively AIs and BIs, and we have a publicly known permutation, okay, then we can actually prove that the BIs are the AIs in permuted order.
Do any of these use the knowledge assumption?
No, not direct. Yes, I think yes they do actually. Yes. I think you might actually, it might be possible to do these without the knowledge assumption as soon as you have knowledge of what is inside the commitments. You might come up with some weird assumption that just says these will actually work without having a knowledge assumption. Okay, so what we have so far, right, is if you look at it from the provers and verifier side, right, so the prover can take some values and commit to those values. The verifier just sees two group elements, right, but it's guaranteed that the prover knows these values A1 through AQ. Okay, we have the homomorphic property, right, so we can take two commitments and multiply them together, and the verifier is guaranteed that what's inside is now the sum of these committed values. We have a restriction argument, so we can restrict to some set. Okay, we can, for instance, say that only the first n values are non-zero and the rest are 0. We have a product argument, so we can have committed values A1 through A and B1 through Bn, and show that a third commitment contains just the product of those values. And we have a permutation argument. We can have two commitments, and we can show that the second commitment contains some permutation of the values in the first commitment. And all of these arguments over here, they're just constant size, right? Constant number of group elements. Okay, so what I want to do now is kind of give the high-level view of how do we put these things together to get a non-interactive zero-knowledge argument. Okay, so what we have is a circuit, and the prover statement is that there's some input that will make this circuit output 1. Okay, and circuit satisfiability is NP complete, so we can do this. We can do all languages in NP. Okay, and I'm using here that n is the size of the circuit. That's the number of gates in this circuit. Okay, so how do we do it? So let me label the wires here. Okay, so I'll call the left entry wire to a gate for A something, the right entry wire B something, and the output wire U something. Okay, so we'll give names to all these wires. And the prover, who knows a satisfying witness, can compute all these input wires, obviously, and all the internal wires in the circuit, right? And the prover will simply commit to those wires. Okay, so we'll say, look, here are the commitment to all the left input wires, here's the commitment to all the right input wires, and here are the commitment to the output wires. And it will give the corresponding CA hat, CB hat, and CU hat, such that the verifier knows that the prover has some concrete AIs, BI, and UI values in mind. Okay? So the question now is, okay, so now we have the commitments to all these wires, right? But how is the verifier convinced that they're actually a valid assignment to this circuit? Okay. So the first step is to actually convince the verifier that it's a correct commitment to bit values on each of those wires. Okay, so remember the group order here is P, prime P, right? So it could be anything from 0 to P minus 1 that's inside these values here. Okay, so what the verifier knows just by seeing the commitments is that there are some A1 through AQ and B1 through BQ and U1 through UQ inside those commitments. Okay, and the prover gives a restriction argument first to show that, well, just committed to values for the first n entries of these commitments and the rest is 0, right? Because, so Q is something larger than the circuit size n.
Why is Q larger than n?
It's going to be used in the other non-interactive zero-knowledge argument, so you'll see later on in the product argument why it has to be larger than n. Okay, and now you can use a product argument to show that the AIs multiplied with AIs is the same as the AIs. The same for the BIs and the same for UIs. Okay? So what this is that AI squared is the same as AI, and the only solution to that is 0 or 1. Okay? So that will convince the verifier now by the restriction argument that are just n values inside each commitment, and by the product argument that each of these n values is either 0 or 1.
Why do you need restriction here? I'm confused. What are the row
It's-
zeros?
So, okay, so let me just go one step back here, right? So here what you have is you have commitments to n values because there are n wires in the circuit, right?
Yep.
And I just want to make sure that there's not more garbage, right? Because these commitments could also have, I don't know, some gn plus 1 to an plus 1 and so forth, right? So I just want to get rid of the garbage. Okay, so what this convinces the verifier is now that these commitments are okay, right? Inside each commitment, there are n bits corresponding to the wires, and these bits are 0 or 1. Okay, so the next question is, do these bits actually respect the NAND gates or not? Right? And we can rewrite that UI is a NAND of AI and BI, so say that 1 minus UI is the same as AI times BI. Okay, this is very useful because with the homomorphic property of the commitment scheme, we can actually get out a commitment to the 1 minus the UI values. So that's just a simple multiplication here. And now we can use the product argument for these committed values to show that the AIs times the BIs is the same as the 1 minus UIs. And this guarantees that all of the NAND gates are okay, right? That the committed bits actually respect the NAND gates. Okay, so there's one more thing that we need. Well, two more things. We need to show that the output of the circuit is 1. That's something you do very easily with a multiplication argument. And then the final issue is that we have to make sure that the wires are consistent with each other, right? So some of the wires appear many times in different commitments. Okay, so one example would be here, U2 is the output of this circuit up there, but it's also the input here, it's also the input here, right? So it appears 3 different places in the commitments. And we have to make sure that all of these bits are the same. And I'm not going to give you any details of how to do that, but I'll just give a little sketch that this is where we use the permutation argument. Okay? So for instance, if we want to show that B3 and B4 are the same values, we would pick a permutation row that flips those 2 values. And then we'll show that CB is the same as CB permuted. Okay? What this guarantees is basically, well, here we have CB, right, where we have B3, B4, and other values. And then after the permutation, we would have B4 here and B3 here. Now, if we have this permutation argument that shows that these are actually the same, then we're guaranteed that, so this is both CB here and CB here. Then it's because those values are actually the same, and those values are actually the same. Okay, anyway, I'm not going to go into the details of the permutation argument, but that's essentially used to show that we have consistent assignment of values to the wires. Okay, so the full argument is something like this. The prover commits to the wires, uses restriction and product arguments to show that all the commitments are valid. Okay, uses product argument to show that the NAND gates are respected, uses permutation and product arguments to show that all the wire values are consistent with each other, and uses a product argument to show that the output is 1. And now the verifier is guaranteed that the circuit is actually satisfiable. Yes.
So you introduced the redundancy to store U2, B3, and B4 3 times, although you know it's the same value.
Yes.
And then you take some care to prove that it's the same value. Why do you not just leave out B3 and B4, but just copy it then when checking the proof? duplicating this.
Right. So yes. So basically, yeah, we're paying a factor 3 overhead here, right? Because they may appear different places. And the reason is because you need some structure in the commitments to do all these product documents. So if I was not to, I don't know, commit to B3, for instance, I wouldn't actually know how to get through the product documents with having some missing value in the commitment for B3 where it was supposed to be.
Because you do all the nuns in parallel. In some
Exactly. So it's because I have to do everything in parallel, right, with these commitments. So if I have commitments to all the AIs and all the BIs and all the UIs, then I can do all of them in parallel with a product document. But if some of the values are missing, then things go wrong. So that's why I need some redundancy there. Okay, so let me show a little details now of how these arguments work. Okay, so let's start with the restriction argument. Okay, so we have a commitment here. Okay, but basically we just have non-zero values when the index I is in the set S. Okay, and outside this set, then the AIs will be 0. Okay, and the proof wants to show that. Okay. And we'll need the common reference string to be able to do this, okay? And the common reference string will be of the form, essentially, so we have the commitment key g and g to the x up to g to the xq, and then we'll have a restriction common reference string to give this restriction argument, okay? And what it will have is basically g to the beta, and then g to the beta xi's for i's in S, okay? Okay, so the argument is just one group element. It's like this, okay? We take the restriction common reference string, we compute h to the r, and then the hi's to the i's for I in S. And if indeed we have this restriction that only the AIs within the set S are non-zero, then it's easy to compute this, right? But if we had, say, an AI outside the set S, then we would be missing the corresponding HI in the common reference string for the restriction argument, and we would not be able to compute this proof here.
So now CRS has a few more generators, right?
Exactly. So this gives a larger CRS.
So they're all the same, the first generator raised to some fixed power.
Uh-huh. Okay. And it's something that's very easy to check. You just do one pairing equation.
Sorry, why does it? Why does the verifier use knowledge of S? So I'm confused. Because the prover could still put more guys over there, right? In pi sub S. So where is the knowledge of S used? I don't see it in the verification equation.
So what you have? Let me just go back.
S is hardwired into the CRS.
So S is hardwired into the CRS in the sense that you only have g to the beta xi's when I is in S,
Sorry, I missed
right?
this point.
And the other ones you don't have. And therefore you can't compute this proof.
So
when you
something
have
that
something
says
outside.
fixed. You cannot dynamically decide on S. S
No,
is-
so S is something that's fixed beforehand.
So going to be the prefix.
Yeah.
Right, always a prefix.
Yes. Okay. So actually, we'll have 3 different sets. Okay? So we'll have one, which is 1 through n. The other one is multiple of n plus 1, so n plus 1, 2, n plus 1, and so forth. Okay? And the third one will be all the indices that are not divisible by n plus 2. Okay? And I'll get back to why we get these particular numbers. Okay? But what it gives us then is that we'll have these 3 common reference strings as part of the series. Okay? So this is actually the full common reference string that we'll be using in the argument, right? It'll contain the key for the commitments, the key for the knowledge commitments, right? And Q is n squared plus 3n minus 2 for some reason. So you see it's quadratic size common reference string, okay? And then we'll have 3 common reference strings to restrictions to respectively 1 through n, multiples of n plus 1, and indices that are not divisible by n plus 2. Okay, and these numbers are, well, basically just because they work, but I'll get back to why we pick these particular numbers. Okay, so what I'll try to do now is to describe the intuition behind the product argument. The intuition behind the permutation argument is somewhat similar to the product argument, so I'm not going to do the permutation argument. Okay, so it'll be useful to think of commitments as commitments to polynomials. Okay, so if you remember the common reference string, the commitment key was G and G1 through GQ, which was basically G and then G raised to powers of X. Okay, and if you look at a commitment, well, it was a product of these GIs raised to AIs, right? Which is really the same as a G raised to a polynomial, okay? Which is R plus, and then sums of AIs times powers of X. Okay, and if you use a restriction argument, then you can guarantee that this is a polynomial where some of the coefficients are 0 and other coefficients might be non-zero. Okay, so you can basically restrict the non-zero coefficients to a set S. Okay. Okay, so now we have 3 commitments, okay? One to AI values, one to BI values, and one to UI values. And the prover wants to convince the verifier that UI is the same as the AIs times the BIs. Okay, and this was what we were going to use. I'm actually going to look at simpler case first, which is also product arguments, but where the B commitment is using multiples of n plus 1 as the indices. Okay. So you can think of this as a commitment with respect to set S1, which is 1 through n. And this is a commitment with respect to S1. And this is a commitment with respect to S2, which was multiples of n plus 1. Okay. So here I have a lot of computations. Okay. So what I'm doing is I'm basically saying let's try to do the pairing of commitment to A values and the commitment to the B values, and do a pairing of the U values with, and this is basically a bunch of -1 values. Okay? And we can interpret these as commitments, right? To commitments to polynomials. So this is basically G raised to this polynomial here. And this is G raised to this polynomial here where we have power of to n plus 1. Okay? And here we also have, this is the CU commitment. And last one here is basically just a bunch of -1s. Okay? So we get these pairings here. Okay? And now we can do a lot of computations here. So this is where we use the bilinear property of this pairing here. Okay, so you can move this thing here outside, you can move this thing here outside, and what you get is essentially G to the G to a product of polynomials. Okay, and then you can do a lot of computations on that. And what you get is product of these two here, okay? So what I have here are the product of this polynomial with this polynomial, where I and j are the same. Okay, and what I have down here are the product of the polynomials where I and j are not the same. Okay, and here we get this mysterious n plus 2 value as well. Okay, so if everything is okay, right? If AI times BI is the same as UI, then the first part will simply disappear, right? Because then that will be 0 for all the I values, and it will just go away. Okay. But there's also some noise. Okay. And the idea behind this argument, product argument, is basically to cancel out the noise. Okay. So the proof will be this thing down here. Okay. So the prover computes that this way. Okay, and that's the proof. So it's one group element. And now the verifier will simply check that what we had up there before, okay, is the same as the pairing of G with the proof. Okay? And if indeed the AIs times the BIs are equal to the UIs, then this first term here is 0, and we just have the second time E and G were paired with some noise, and this is exactly the proof. So it works out, right? So that gives us completeness. Okay, the prover will give some more information. So essentially this proof here, that's restricted to the set S3. Okay, and this is something the prover will actually prove to the verifier. Okay, so remember the proof was this complicated formula. Okay, the prover will demonstrate that it knows all these values that has been used in generating the proof by sending pi hat. And it will give a restriction argument, okay, to the set S3. And this is possible because n plus 2 only divides this jn plus 1 plus I term when j is equal to I. So this is kind of where the magic comes in. Okay, so now we have a proof, and the prover has given a proof that the proof is restricted to the set S3. Okay, so let me argue that this gives us soundness. Okay, so the verifier looks at the verification equation, right? And by the previous calculations, we know that this is the same as the first time term here, right? And then G paired with some noise. And all of the noise is in S3, okay? And then it's G paired with a proof, and all of the proof is in S3 as well, because that's the restriction argument that was given by the prover. Okay, so the point now is that the noise and the proof pi, they're restricted to set S3. And the set S3 corresponds exactly to the coefficients of x to the L, where n plus 2 does not divide L. But what we have in the first term is exactly the case where L is divisible by n plus 2. So you can say that these two parts, this part here, this part over here, they don't interfere with each other. And that's the reason that we picked S3 as a set where n plus 2 does not divide L. Okay. So what you can do is you can use the Q computational power Diffie-Hellman assumption to say that, look, the only way this is possible is actually if the first part here is equal to 1. Because the noise doesn't interfere, it has different powers of x. Okay? And you can actually go further with the Q CPDH assumption and also show that this implies that for each individual n plus 2 multiple of xi, that ai times bi is the same as ui. So we actually get from this that for all I, we have ai times bi is the same as ui. Okay, so that was a lot of work. Essentially, the idea underlying this argument is that we have some polynomials. By doing careful restrictions, careful products of polynomials, we can get different terms to cancel out with each other, eliminate different terms, right? We can isolate these things that we're actually interested in, the AIs times the BIs are the same as the UIs.
Is it clear that you need polynomials? I'm trying to see what properties of polynomials did you really use. I mean, it seems like you just need some, you know, I don't know, some numbers which, I don't know, resist some calculations.
That may be true. There might be other ways that you can go around it.
Polynomials, because different terms interact with each other.
Right.
You have an x to the 1 and an x to the 1, you multiply them, you get the coefficient that goes into the x to the 2 bucket. So it does behave like
Well,
that.
no, I see that you sum, it's just it wasn't clear that polynomial is exactly the right thing.
If you wanted to prove that U is a product of the polynomials A and B in the other sense, that say U is the coefficients on, I guess, n squared of the polynomial that is the product of the A and B, that would be simpler, or
I don't know on top of my head. Okay, so what we have now is we have a constant group element proof, or argument, that these committed values, AIs, BIs, and UIs, that the UIs are the product of the AIs and BIs. Okay. I did have this problem that I looked just as a case where the BIs were committed in S2, right? But you can actually use the product argument to translate between sets, okay? If I have here some values committed in S2, and here some values in S1, and I do a product argument with ones, then I guarantee that the BIs and the UIs are the same. So I can translate between S1 and S2 using this. Okay, so I can have a set of commitment to values in S1 and commitment to values in S2. I can show that these values are the same. Okay, and that will give us product arguments for commitments where all values are in S1. Okay, so the full non-interactive zero knowledge arguments consist of giving knowledge commitments, restriction arguments, product arguments, and then also some permutation arguments, and all of these are constant size. Okay, and that gives us a very short non-interactive zero knowledge argument. Okay, the only problem here is that the common reference string is n squared size. Okay, it has n squared group elements. I want to briefly talk a little about Lipman's recent paper, TCC. Okay, so what he did was he reduced the size of the common reference string to n to the 1 plus something small. Okay, so getting close to linear, not linear, but somewhat in that ballpark. Okay, and essentially what he does is he chooses the powers of x in a more clever way. Okay, so you can generalize what I did a little before, right? So I had commitments in S1 were with respect to S1, so that was x1 through xn, okay? And then multiples of n plus 1 in S2. More generally, you could use x to the powers of kappa i's and x to the power of lambda j's. Okay, and the question is now, can you choose those in a more clever way to give a product argument? Okay, so he still uses the same verification equation. Okay, you can do the same calculation as before. Now you have when powers of x to the kappa I plus the lambda I here, and then you have some noise. So it's pretty much the same thing, right? And the question is basically, when do you have non-interference between these powers of x and the noise? Okay, and you have that exactly when these powers of x do not belong to, not be written as one of any of the powers appearing here. So we have x to the 0 here, right? Here we have x to the kappa I primes. Here we have x to the lambda j's. And here we have some sort of kappa I primes and lambda j's where I prime is not equal to j. Okay, and if we can ensure that the terms we have here do not appear in the noise, then we're happy. And he found a way to do that with progression-free sets. Okay? So essentially we want to avoid this appearance here. And he picked a progression-free set. Okay, so he actually picked the kappa i's to be equal to the lambda i's. Okay, so the kappas and the lambdas are the same. Okay, and then you can pick a progression-free set, which is a set such that 2 times lambda I cannot be written as lambda I prime plus lambda j, y prime not equal to lambda j. Okay, and if you do that, well, if the lambda I is the same as the kappa I, right, then the question is basically, do we have x to the lambda I plus lambda I belonging in this set? And if it's a progression-free set, no, that cannot happen, right? It's because 2 lambda I cannot be written as this thing here. Okay. And it turns out that you can actually choose pretty small progression-free sets. You can have them down to the size of n to the 1 plus something small. And that gives you a much more compact way of having these commitments and still have the non-interference between what you want to prove and the noise. So there were also some other clever ideas in his paper with the permutation argument, but I don't have time to get into that. Okay. So what we have now, what I've talked about so far, is what we have. We have this constant side non-interactive zero knowledge argument with n square group elements in the common reference string, right? And we can use, to get better efficient, we can use a constant side group, constant side non-interactive zero knowledge argument, and then with the close to linear common reference string, but not linear. Okay. I'll talk a little about how to balance these things. How can you balance the common reference string with the size of the non-interactive zero knowledge argument such that both of them are sublinear in the circuit size? Okay. So essentially what we have here is we have a very long common reference string, right? It's quadratic in n. Okay, and then we have some commitments to what's inside these wires. And if we have a shorter common reference string, well, the problem is that we cannot commit to all the wires at once. But what we can do is we can simply make several commitments, right? So now I make many commitments. Each of them contains some block of the wires. Okay? So that's what we have here. And you can basically think of this as this vector of commitments as a commitment to all the wires, right? And you can operate independently on the first commitment, on the second commitment, and so forth. So you can still do the restriction arguments on those. You can still do the product arguments on them. Okay. The only problem that remains is the permutation argument, right? Because the permutation may actually go across these commitments, right? It might be that something appearing in the third commitment now suddenly appears in the first commitment, and so forth. So it all gets mixed up. Okay, so you need some permutation argument to go across all the commitments and actually make permutation over all the commitments, all the n values, even if they're committed in different commitments. And you can do that by putting in basically a permutation network. Okay, so basically you build a permutation network and you use the permutation arguments for the commitments to go through this permutation network, and that gives you the full large permutation. So you build a large permutation from many small permutations. And if you do this balancing, then you can get down to something where the common reference string and the size of non-interactive zero knowledge argument are the same, right? So you can get something that's sublinear. So in my case, something that's n to the 2/3, n to the 2/3 for both the common reference string and the argument. And in Lipma's case, you can get almost down to the square root of n. Okay. So what we have now is these public verifiable non-interactive zero knowledge argument for circuit satisfiability, and we actually have this sublinear size without using random oracles, but instead using this knowledge of exponent assumption. That's it. Thank you.
Questions? We asked enough during the talk, I guess.
Yes.